This conference will now be recorded.
Okay, great. Hello guys, and welcome to the third lecture of this course. And today we will talk about I would call it classical methods for dependability analysis. And we mostly will cover the methods for analysis, not of all dependability characteristics, but we will mostly focus, as I taught in some previous lectures, on reliability and safety. So today I will talk about several groups of methods that can help you to evaluate how reliable is your system. And these methods, we will talk about three groups, basically component level reliability metrics. This would be our basic metrics that can be applied to atomic or indivisible components. And basically, these are the ways how we can represent how reliable is a single component. And there are different probabilities of failures, mean time to failures, failure rates, and so on. Then we will talk how to compute or how to evaluate the reliability of the system that consists of several components. And here we have different reliability block diagrams, fault trees, and I will also cover some Markov chains and pattern nets. And finally, I will talk about more high-level methods that I usually mention in, or not mention them, but required by the safety standards and the methods. In most cases, this failure mode and defect analysis. We will not have, deep dive into the FMEA. I'll just cover it, and I also compare it with another method. It's called hazard and probability analysis. But most of the focus basically will be on these first two parts. So, but as usual, at the beginning of the lecture, I'm giving some example of the disaster.
RB hydraulic power unit.
So I'll better switch off the audio here. It is so-called the Challenger disaster. It is a classical failure that you can find in lots of books about the dependability analysis and so on. In the first two lectures, I was also talking about failures of space system, but the difference was that in that examples there were only the damage of a spacecraft and the mission, and here it was the loss of the crew. So 7 astronauts were dead because of this failure. So, and it happens in Florida, Cape Canaveral, January 28th, 1968. 86, sorry. Yeah. So I'll just show basically everything went well, and then it was an explosion somewhere here. You can take a look on this video. So yeah, you see big explosion. So, and now basically for us it's interesting what's happened. So on the next slide I have also an animation that basically shows what has happened. So this is one of the side thrusters, and on the side thruster there is so-called O-ring that basically keeps the things together, and it was a damage on this O-ring, and because of this damage a jet of this burning fuel, because of this damage in the side thruster, this jet gets out. Just wait for it. So, and basically this jet blown up the main fuel tank. So, and this was a mechanical failure. Let's say it was the failure of this O-ring and of this jet, but this wasn't such a simple one. It's also the problem was because the start was in a quite cold day, and the temperature condition of the start violates the requirements. So the system should be started with higher temperature, but nevertheless it was decision to start the mission on this day, and this was one of the reasons. So at the end of this lecture, we will also cover a special technique called root cause analysis. This technique is not about the evaluation of the reliability of the system, but more about to find out why it has happened. So, but it's also used a lot in the reliability, not analysis, but we usually do it post factum after something has happened. So, and I will show an example of this disaster at the end of the lecture. So, okay, some recall from the previous lectures. We are still talking about the dependability, and the dependability is still defined as the transversiness of a system, such that reliance can justifiably be placed on the service it delivers. So I recommend you, if you haven't read yet, I recommend you to take a look on this dependability basic concept and terminology by Laprie and Tavi series, because this is a kind of the main source where I'm taking the definitions for different dependability connected terms, which we have discussed on the previous lecture. Dependability tree. And today we will mostly focus on the attributes, and we will mostly focus on the reliability and safety. So we will learn how to evaluate reliability and safety of a system. Okay. Another piece of the recall, model-based system engineering. This figure we have discussed it on the previous lecture, and this part is a model-based analysis. So we analyze the system properties based on the information which is stored in the system model. So, and we're talking about the dependability analysis. That's why we store the information about the system components, about the reliability of the components and reliability of the system. We can compute based on the models of the system in a model-based way. Okay, and this is a kind of simplified version of the model-based dependability analysis, and this is a little bit more, I would say, more advanced, or I would say a little bit more complicated version of that with some references, but it also covers only few methods for reliability analysis. Basically, these main models which we were talking about, like Simulink, UML, SysML, etc., this is this block. In order to perform the reliability analysis, we need to have not only the model of the system, the structure or behavioral model, but we also need to know the reliability of the single parts or of the components of the system. And this we're doing with this block using the component reliability metrics. And we say that, okay, this block in the SysML diagram, it represents a sensor, and the mean time to failure or probability of failure of this sensor equal to 0.0000, some zeros and one in most cases. But it's not enough to evaluate the system. We need to apply some system level models. And an example of this is a static fault trees, which are used anywhere, everywhere in industry. And there are a number of ways how to automatically create static fault trees from the baseline models, from AADL, from Simulink, from SysML, and so on. And it's also not enough. We have the fault tree, I will talk about them later, but we need to do the computation. And the computation also can be done in various ways. We can use either direct bottom-up, top-down approach. We can use mathematical methods like Bayesian diagrams, or Bayesian binary decision diagrams, or Bayesian networks. And after that, we can compute the reliability metrics of the system. So, and I will also cover some specific methods based on the Markov chains and model checking. And these I would call them advanced methods for reliability analysis. We'll cover them later, not on this lecture. On this lecture, we'll mostly focus on the classical method. So, for example, the most classical way, okay, We generate fault trees. From the fault trees, we get the reliability of the system. But there are also some other methods. Let's talk a little bit about the history, about the methods, standards, and tools for the dependability analysis. So in this slide, you can see an example of safety critical systems. So, and all of these systems, they need the reliability analysis. There are safety standards that tell us, okay, if you develop a car, plane, even for the military, of course, and for automation, industrial automation, for medical robotics, for space, for all of these systems, we need to fulfill the requirements of safety standards. And these safety standards tell us before the system goes to the production, you need to analyze how reliable the system is. Here is a history of the methods which are connected to the reliability. Let's say a long time ago, Laplace has proposed the Bayesian probability and Andrei Markov has proposed Markov chains. This was not in the context of reliability, of course, it's just mathematical models, but these models are used for reliability analysis a lot. That's why they're here. Then from 1939 to, I would say, 1960s, 70s, there was so-called golden era of the reliability analysis, because in that time, the mechanical system, complex mechanical systems started appearing, and it was the requirement, or it was, we need to analyze the reliability of this system, and main methods for the reliability analysis were invented during this time. It includes FMEA. It was from military of the United States. It was reliability block diagrams, fault trees, HAZOP, root cause analysis, application of Markov methods for reliability analysis, all the things that were proposed during this time. And the difference is, during this time, most of the methods, they were static, because during this time, the systems were, as I told on one of the previous lectures, they were, big, mechanical, stupid. There were not so many brains in the system. And in the 90s, the software comes in play, and actually before, but let's say in 90s, the software really became a central part of most system, and the system, because of that, became more dynamic and more intelligent. And already in the 90s, it was not enough to use just a fault tree to analyze the dynamics of the system, and that's why the dynamic methods have been proposed. And for example, dynamic fault tree and application of the Markov models also, it was another step on the application of stochastic models and Markov chain models during this time. And then, of course, in 2006, cyber-physical systems were proposed. And now it's a kind of nowadays, actually, even the methods that were proposed in the 90s are not really enough to analyze the reliability of cyber-physical system in an acceptable way. And that's why we have all these model checking techniques and so on that I will also tell about. But today, mostly we will focus on the classical methods on this part. Okay. So that's actually what I have talked about on the previous slide: mechanical and electromechanical system, mechatronic system. Now we have cyber-physical systems. I also already talked about the standards. There are standards that tell us that we need to analyze the reliability of the system. The standards can be subdivided into the international standard, regional standard, and national standard. International, it is worldwide. Regional, for example, European, American, Asian, and national is for particular countries. So I'm living in Germany at the moment, so there is a German Institute for Standardization. But in most cases, the standards are created as international standards, and then they're adopted as a national standards. The standards that deals with reliability of the systems which we are talking about, in most cases, these are the standards of three main organizations: ISO, IC, ITU. All of them are based in Geneva, and they were created long time ago, but still, for example, ISO 26262, it is a safety standard for automotive industry, which is used nowadays, or IEC 61508, it is a safety of electronic and electrical components. And basically there is, even between these standards, there are a lot of similarities. And then for example, this standard, can be adopted for the region, or it can be adopted for Great Britain, for Germany, and so on. Now about the producers, I'm not, let's say, this is not advertisement, so I'm just showing that there are a number of companies that can sell you the software which you could use for the reliability analysis. Usually this software is quite expensive, and most of the companies, they have preliminaries the same set of the software. They have fault trees, reliability block diagrams, simple markup chains, and so on. So the prices are different, the conditions are different. So, but basically the prices are quite high because there is not a big market for the reliability analysis. So only, you know, several guys in each company is doing the reliability analysis. That's why the software is rather specific and rather expensive. However, I believe that the main income of these companies is not by selling the software, but even selling the service for the reliability analysis, as far as I know. Okay, let's come back to the classical methods. As I told, I grouped them into the three parts: reliability metrics of individual components, system-level reliability models that can be built on these components, and to compute the reliability of the system, we must use the reliability of the components, and guidelines, processes, steps, and so on, like a FME that demand to do the system-level reliability analysis. Reliability metrics are used in the system-level reliability models. Reliability models are demanded by the guidelines. That's the idea. The reliability of the components is the probability that it will adequately perform its specified service for the specified period of time under specific condition. This is the definition of the reliability, and that's what we'll continue with. Now I want to also give some basics of the theory of probability, because we will use it a lot. But it will be just, you know, crash course to the theory of probability. First, what is probability? Basically, it is a number from 0 to 1. Please do not use like the probability 100%. Let's leave it for the, you know, for the marketing guys, for engineers here. For us, probability is a number from 0 to 1. Probability in the real world, there are no events with probability 0 or no events with probability 1. So, okay, maybe it's something, but let's say probability 0, it means that event will never occur. And probability 1, it means that event will for sure occur. And usually we have something in between. And usually we have something either close to 1 or close to 0. For example, the probability of faults, they are usually very small, very negligible, and they are somewhere here. So in most of the systems, the probability of failure, for example, during the system lifecycle of some years, would be 0, like 5 or 6 zeros, and then 1 or 6. Yeah, 5 or 6 zeros. And let's say 1 minus this probability, we will the probability of failure, the probability of correct mission. Let's say if we are developing the system, usually there is a high demand of the reliability, like 5 nines, 6 nines, 7 nines after the comma. And that's why the reliability will be close to 1 and probability of failure is usually close to 0. Nevertheless, we must work with these numbers and we must compute them. Now some notations. P of A, the probability of A, where A is a stochastic event. P of A given B, the probability of A given B occurs. This is a conditional probability. We have two stochastic events, and we compute the probability of A after event B is occurred. That's how we denote it. P not A, or sometimes we do this no like as a line on top of A, and this is basically a how it's called, formula of complete probability. The idea is that the probability that event will not happen equals to 1 minus probability that this event will happen. So, and the probability of not A, or that A doesn't occur. And as you remember, the reliability, in most cases we define it, reliability as the probability that system will survive under specified condition during specified period of time. Okay. Now I want to show you this visualization, and I will come back to that from time to time, because from my experience, it's really well understandable visualization of these stochastic events, like the tree. And I will explain it maybe a bit later, but here I want to say that here we are talking about two events. These events either can be consequent in time, like first event A and then event B, or it might be that we do not care about the timing and we just care about these events happens. Okay. Imagine that we are staying here and event A will happen. And you can imagine, like, you know, the theory of multiverse, like in each period of time, our universe is divided into several universes, and there are different outcomes in each universe. This is exactly the same thing. For example, we have two components in our system, like motor A and motor B. We have a plane with two motors. And the plane can fly with only one motor, it's fine. If two motors are down, we crash. Now imagine that the failure of motor A, motor 1 is event A, and the failure of second motor is event B. We know the probabilities. From some books we find that the probability of failure of motor A is 0.001 and the probability of failure of motor B 0.0 something else. So we are flying, everything fine. With probability P of A, we jump here. And here it means that if we define A as a failure of motor 1, we are flying only with the one motor in this universe. Here we are flying with one motor. Here we are flying with both motors and everything fine, okay? And then there is the second event, is the failure of the second motor. And the failure of the second motor is, in this case, we are using the probability of failure of the second motor given that the first motor is already failed. If these motors are completely independent, then probability of failure B given A will equal to the probability of P of B given A will be equal just to PB if they're independent. But it might be that they are dependent because of the failure of the first motor, the second motor will have higher load, and the higher load means higher wear out, and the probability of failure of the second motor, of motor B, can increase because of the failure of motor A. That's why, for example, the probability of B here might be higher than the probability of B here, okay? Hope you follow me. And we have two motors. Both motors can be either failed or not. And in this case, we have four consequences. Both motors failure, motor B failure, motor A is failed, and both motors are not failed, okay? And that's how we will visualize it. Here you see, we just start, both motors are okay, and with probability PA, motor A will fail or not, and we are here. If not failed, we are here. Then we have probability of B given A and probability of not B given A. And finally, we end up to some universes. Here, both motors are failed and we are done. Here and here, one motor is failed, but we are flying on erroneous condition, but we still fly. And here, everything fine, both motors are okay, we landed, we are mission accomplished. So, but if we don't care about the about the sequence of events, at the end we might be interested on these probabilities: probability A and B, probability A and not B, probability not A and B, and probability not A and not B. This probability means the fact that A hadn't happened and B hadn't happened. So, and these are different. So this is the probability that outcome of our mission, that everything was fine. And this is the probability that B not fail after A not fail, or in condition that A not fail. Okay, I think I will come to this with some examples. This will be explained, but please keep in mind these three because it's really helps a lot. So, and our A and B, the failures in theory of probability on the statistic, it's called statistical experiment. And the feature of the statistical experiment is that we can say that this is a statistical experiment if it has more than one outcome. In our case, it is fail or not failure. Each possible outcome can be specified in advance. So we can say that during our flight, the motor can either fail or not. We can specify it. And the outcome of the experiment depends on chance. Now we are talking about the random faults of the motors. They are for sure depend on chance. And that's why our event A and event B are either statistical events or statistical experiments. So if we are doing it as experiment, we can call it experiment. Now, let's talk about how we can estimate the reliability of the system component or the probability of failure. Okay, imagine that we have 10 items, for example, 10 sensors. And we can run these sensors for some time. We can define that we have a system lifetime of 5 years. And we can run this sensor or get some data from our customers from 5 years. And we know that sensor 3 has failed after 1 year, and sensor 6 has failed after, let's say, 1.5 years. So it might be that sensor 9 will fail after our system lifetime. This can be, but it's not. Actually, all the sensors will fail eventually. We don't know when, but they will fail eventually. But we are interested about the probability that the system will survive this interval, because the probability is that the system will perform its function during specified service during the specified period of time. This is a specified period of time. We are interested how many items have been failed during this system lifetime. Here is only 2. That's why we can estimate that the probability of failure is 0.2, right? 10 items, 2 failed, 8 survived. Okay. So, and the probability of failure basically is a very simple reliability metric. We can say, if someone asks what is the reliability of the system, you can say, okay, reliability of the system is 0.999. And you are saying, this is the probability that the system will survive during the time under specified condition. There are other examples, we'll go through it, and there are lots of them. Average number of failures, mean time to failure, mean time between failure, mean downtime, failure rate, failure in time, bit error rate, and etc. So the message here that there are different ways how to represent the reliability of the system, not only the probability of failure. I would recommend this book, and basically the first part of this lecture is based on this book. So, and it is probabilistic methods and statistical methods for reliability. Okay, Now let's talk about other metrics such as MTTF, mean time to failure. And mean time to failure is defined as the length of time a component is expected to last in operation. And FTTM is one of many ways, I already told it, and MTTF can be computed like a sum of times to failure of the components divided to the number of components. Okay, we see here, like here time to failure was 1 year, here time to failure was 1.5 year. Here actually we don't know, but we could say that they survive, so we could say that basically to identify time to failure, we should not take these guys into account. We should take only these guys into account. And this guy we also need to take into account if we want to identify MTTF. In this case, I will take this time plus this time plus this time divided by 3. And this would be my estimation of the MTTF. You have a correct service, you have an incorrect service, and this is a kind of average MTTF. So, okay. That's what I was already talked about. We have the system lifetime, and we know that, okay, it is another example. I took it somewhere from internet, from one of the sources. We have 4 times to failure, and one component has survived after the time to termination. So that's why we exclude this component and we compute MTTF only based on these 4 components. Okay. Now MTTF is so-called simple failure model, and in contrast, we might have renewal failure model. What does it mean? It means that the system can be recovered after the failure. And in this case, we will talk not about MTTF, but MTBF, mean time between failures, which refers to the average amount of time that a component functions before failing. So here is the visualization. The component was okay, then it was failed, then it was on the failure state some time, it was repaired to the normal condition, and then it was failed again. And basically this is the time between failures. But be careful, in some literature, this mean time between failure takes also into account this mean time to repair, and in some literature it is treated separately. Usually, but not always, this unit of measurement include only operation time between failures, this one, and does not include repair time. The item is repaired and being functioned. However, not always. Okay. MTBF can be computed as operating time divided by number of failures. Simply like this, but operating time excluding MTTR. And if I already started talking about the MTTR is usually not the measure of reliability, but it is the measure of maintainability. I'll just come back. As you remember, here we have several attributes, and in most cases we are talking about reliability, but there's also maintainability. It is the ability of the system to be recovered, to be recovered. And actually, mean time to repair is a very commonly used measure of the maintainability. Okay. MTTR tells us the average time required to repair and return to the working status. MTTR can be computed using this formula: total time spent in maintenance during the system lifetime, total number of maintenance activates conducted. So, and this structure, okay. And actually, if we are talking about the attributes, you remember there was also not only a maintainability and reliability, but it's also availability, its readiness for the correct service, and it also can be computed using MTBF and MTTR. If we divided MTBF on this MTBF plus MTTR, we will get the measure of the availability. Now, probability of failure, mean time to failure, this is basically only one number. But sometimes we are interested how the probability of failure changes over time. And this can be represented using continuous failure rate models, or just called failure rates. You could see some figure here, and it's very interesting that they are quite different for hardware and for software. Let's start with the hardware. In most cases, it's called bus to curve, you know, like bus where you wash yourself. So, and that's how the probability of failure changes over time. So here we have the failure rate. Failure rate is the frequency with which an system component fails. It is expressed in a failures per unit and usually denoted as a lambda. For example, it can be a number of failures per second, number of failures per year, number of failures per 10 years, depending on our time intervals. So if we are talking about, let's say, several years of operation, we might talk about hours, for example, number of failures per hour. Of course, this number is some close to zero, like zero, something, 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 but it changes over time. Why it changes? So this is the sources for this plots. Why it changes? Because this plot, it consists of several plots, basically several reasons of failure. They are accumulated into this plot. The thing is that the hardware system, usually it fails either at the beginning of the life or at the end of the life. At the beginning, because of so-called, you know, infant mortality, they called, or, you know, the system was not well tested, I would say, or it was just faulty system which was not tested enough. And that's why the system can fail at the beginning of the operation. And here is the rate of the early infant mortality rate that goes down with the time. Then it is a constant failure rate because of the random failures that can happen just randomly in any time. And also there is another curve that shows how the system wear out, become older, older, and older. So it could be some corrosion, wear out of the connectors, and so on and so forth. And if you sum up all these plots, you will end up with this one. And that's the reason for this bus curve failure rate. Now let's talk about the software. It's a completely different story. In the hardware, we have most cases random faults. In the software, we have systematic faults. That's why we have some bugs in the software when it is released. And then we find these bugs, we test it, and we debug the software, and the software becomes better, 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 and better. The failure rate drops down. And then we decided, okay, the software is obsolete. We need some new version of the software. We need some new functionality. We write new code. What means new code? New code means new bugs. And we have the drop of reliability after an upgrade. Testing, drop of reliability, testing, drop of reliability. And at some time, the software becomes just obsolete and we are not using it anymore. That's the failure rate of the software. Because the failure rate is really small number, it's usually reported as FIT, failure in time, and failure in time is defined as a failure rate per billion hours. It basically means we take the failure rate per hour, multiplied by 10 power 9 billion, and we get FIT. Difference between continuous failure rate, continuous models, and constant models. Constant models are good to represent the constant failure rates. But if the system is really dynamic and there is different probabilities of failure, for example, let's say we have our drone takes off, then flies, and then lands. And during the takeoff, the motor has higher load. And even during the mission, the probability of failure in the first mission phase will be higher than in the later mission phase. That's why if we would like to express this in a good way, we need to use failure rate. But for the components which are work, let's say, more or less constantly during the lifetime, we use MTTF, MTBF, and so on. There are places where we can find these numbers. In most cases, it is FIT and MTBFs. The places are for the electronic components. It is Military Handbook, RDF 2000, FIDES. For the mechanical parts, it is MPRD, and also there is EPRD, I believe. Yes, EPRD. FIDES is a trend nowadays. It is used a lot. So basically, these are kind of, handbooks where you can select, okay, I want to know the probability or MTBF of specific sensor, and there are basically formulas, and into these formulas you enter the conditions, like, for example, operation time, operation condition in terms of temperature, radiation, some parameters of the sensor, and so on. And this formula helps you to estimate, for example, mean time between failure. This will not give you 100% or very precise reliability of the component, but when we are talking about the risk analysis, about reliability analysis, we must accept that we will never have exact numbers. All what we have, just some preliminary numbers, but we need to do this analysis using the numbers we have. And these books or these methods, there are the best estimation which we currently have. Here we talk about the hardware, about the software, and about this thing. In most cases, the faults of the software, they are static, systematic, sorry. They are not random. The bug is either in the software or not. And therefore, in most cases, in most standards, or in most industries, there are quite hard requirement for the software testing, but after the software is tested, we assume that it is perfect. Of course, it's not perfect, but let's say we cannot model systematic faults using stochastic methods like MTTF and so on. Therefore, stochastic faults. Inherently, such kind of the probability of failure, mean time to failure, inherently we expect that the cause of the failure is some random events. But if this event is not random, it makes no sense to use the theory of probability for that. And that's why in industry, most of the software is assumed to be perfect. However, there are some special repositories where the guys try, to compute the probability of failure of the software depending on how big is software, how tested is software, and about lots, and there are lots of different methods, like, for example, the simplest one, okay, the more complex software, more bugs we have, and they try to call, it's called, curve fitting. They try to fit, okay, they have lots of the software products, they measure, for example, lines of code, and they know how many bugs were detected, like different trackers, and then they try, to curve fit, saying, okay, if we have 1,000 lines of code, we have 10 bugs. If we have 10,000 lines of code, we have 100 bugs, and so on. But this is more or less curve fitting, and usually it's not used in the industry. To this course, we also have the exercises, and then the exercise, in the second exercise, we will do the fault tree analysis. And I would recommend this MTBF calculator by ALD. I only recommend it because it's free. You can download it, it's Windows only, but it works pretty well. This is a kind of the tool that gives you an access to the standards, including FIDES, including NPRD. And for example, I can select here, okay, I want to know the probability of failure of electronic component. I want to take it from FIDUS. I will select IC digital because I want to know the probability of the controller. Then it might be another window, and I tell, okay, it is a silicon, it is a FPGA or something like that, number of pins, blah, blah, blah. I specify the temperature, and boom, I have mean time between failure, which is 1.45340 hours. So it's quite reliable piece of the hardware. Can be downloaded from here. Here's the guide how to use. So this is the source where you can easily get some preliminary estimation of that MTBF for most of the components you have in your system. More, I would say, more precise results or more precise numbers you can get from the websites of the producers. For example, Texas Instruments, in their website, they have this calculator where you can also define, for example, application temperature and so on. But here you also have to be careful. This is a producer of the of this equipment. Most probably, the reliability, which is reported on their website, would be really good. I'm not sure, but just my expectation now. And sometimes you just can find it in the specification. In most cases, in the specification of a sensor, controller, actuator, or something, you will find at least one line which tells about MTBF or FIT. Sometimes it's not really precise, but again, to analyze risk, we need to have some sources from somewhere, and it's better to have something than to have nothing. If we have something, at least some estimate we can make. Okay, good. And following this idea, I want to say that I will jump to the second block, system level reliability models. And this is how we compute the reliability of the system based on the reliability of the component. And here I would say, okay, now we will compute the reliability of the system based on this reliability of the components that we took from FIDUS or something. The result of this analysis would be as good as precise are the inputs. That's why sometimes it is more important to know these inputs in a more precise way, because let's say the next things, they are technical. Here we have, here we have some, let's say I would say some magic. So we don't really know the precise things. These methods, they are precise, they are mathematical and so on. There is nothing unexpected things on these methods, but all the magic happens here. Okay, whatever. We know our system, it consists of some components. We know the reliability of our components. We need to compute the reliability of the system. We can use reliability block diagrams, fault trees, event trees. Let's start with reliability block diagrams. It is a very old concept, and here you can find some information. The idea, RBD is a graphical representation of the system components and connectors. Basically, here is input, here is output, but you should not treat it like, for example, input of the signal. The main idea here is serial and parallel configurations. What does it mean here? If the components are in parallel, it means that they are redundant. We have two motors in our plane, and with one motor we have survived. If we have, for example, I don't know, we have a system with sensor, controller, and actuator. We need all of them to survive. In this case, they will be connected in sequence. And the system survives if we have at least one pass through the system. I mean, for example, if component 2 dies, we can use component 4 instead, and we will go like that. And if, for example, all the components from here dies, or if the component 3 dies, we still can go through the component 1. I mean that the component 1 is redundant to entire system like that, and component 2 is redundant to the component 4. This is what's important, okay? So if at least one pass through the system exists after the failure of the components, then we are still okay. That's the idea behind the reliability block diagram. As I told, we have The reliability block diagrams consist of two patterns: sequential configuration, parallel configuration. Let's start with sequential configuration. System function if and only if all of its components function. For example, we have sensor, controller, actuator. If sensor fails, the system fails. If controller fails, system fails. If actuator fails, system fails. And that's why we have a system configuration. Here with this formula, reliability of the system, and here reliability is the probability that the component or the system will survive during the mission time under specified condition. Here we just need to multiply the reliabilities of both components, or 5 components and so on, n components, to get the reliability of the system. If you remember this tree, which I have proposed before, let's say, is it possible to do some drawing here? No, I don't think so. So let me just come back to this slide, which was in the very beginning. So imagine we have two components, component A and component B. If they are connected sequentially, the failure of each of the component means the failure of the system. If component A fails, we already failed. I mean, if we are here, we already failed. But if component A survives, still component B can fail, and we also will be failed. And only if both components survives, the system is okay. That's why, and now I'm telling about how the probability of such kind of thing is computed. We have PA and we have PB given A. In order to end up here, we need to multiply this probability to this probability, okay? And in order to end up here, we need to multiply this probability to this probability. So if we will do like this, the sum of the probabilities of n events of these ones will be always 1. Because, okay, here all the probability, okay, here we have the probability equal to 1, and it is divided like 0.1 here and 0.9 here. And this 0.1 is divided, for example, to another 0.01 here and 0.09 here. So if we will sum everything up, we'll have 1 here. But if we have the connection in sequence, the only way the system survives if both parts are survived. That's why we multiply the reliability or the probability 1 minus failure, 1 minus probability of failure of A to 1 minus probability of B given A. And then we end up here. That's why here we have the multiplication of the reliabilities. Now the second configuration, parallel configuration, we have the redundant motors, 2 redundant motors, and we still can fly with 1 motor. In this case, we survive, if you remember this tree, if all these 3 dots on the right side, if we end up on these 3 states on the right side, then we survive. And in this case, we computed with another formula. And here we do this trick. We are interested on not on the, we represent the reliability of the system as 1 minus Q, and Q represents the failure of the system. And now we are talking not on the right branch of this tree, but on the left branch of the tree, because the system will fail if both components fails. And that's why we multiply the probabilities on the left part of the tree. And these are the things here. And then we represent each probability of failure as 1 minus probability of not failure. And that's why we end up with this formula. So basically, if I have a system, we can represent it using the series and parallel configuration. And then by computing this formula, for example, we can compute it like bottom up. We can first compute the reliability of this subsystem of these 2 components using the formula of parallel configuration. Then we can compute the probability of this part using the series configuration of this one and the result which we got here. and then we will have the system of parallel configuration of two components, and we use the parallel configuration again. Okay, I think this is quite clear. So dependent failures. There is another special gate in the reliability block diagrams and also in the fault trees I will talk later. For example, we have 3 motors in our plane and we need at least, okay, it's strange plane, but whatever. We have 3 motors in our plane and we need at least 2 motors to survive. In this case, we will use this block 2 out of 3 block. And if the failures are not dependent, for the independent failures, it can be represented like this. If component 1 survives and component 2 survive, it's fine. If component 1 and component 3, it's fine. If component 2 and component 3, it's fine. So one of these configurations should survive. So in this case, that's how we model. It's K out of N parallel configuration. There is a reliability standard that tells us how to use reliability block diagrams. There are some vendors that produce the software for the reliability block diagrams. Let's go next. Let's talk about the fault trees. So the fault trees are another way how we can compute the probability of the failure of the system based on the probabilities of failure of system components. It's very similar to the reliability block diagram, but it's, you know, it's a kind of negotiation, how it's called. It is, let's say, it is similar from the concept, but it is opposite in terms that in the reliability block diagram, we are usually computing the reliability of the system. And with the fault tree, we are computing the probability of failure. It is another logic. So in the reliability block diagram, we are thinking how we survive. And in the fault tree, we are thinking about how we fail. But in the industry, in most cases, we are using the fault trees, not the reliability block diagrams. So FT fault tree is a graph. It is directed uncyclic graph. The graph has 3 kind of nodes. Top event, in most cases, represent the failure of the system. Basic events, in most cases, represent the failure of system components. Logical gates explain how the components are connected, either sequentially or parallelly from the reliability, from the redundancy point of view. For example, this part of the fault tree, it means that this part of the system fails if both component 1 and component 2 fails. And this part of the fault tree represents that this part of the system fails if component 3 or component 4 or component 5 fail. Okay. RBD's fault trees are interconvertible. This RBD can be presented as this fault tree can be presented with this RBD. Both using RBDs and fault tree, we can identify so-called minimal cut sets. And this is a traditional solution for the fault tree. So the minimal cut sets are all the unique combination of components, component failures that can cause system failure. Here is an example. Here is the minimal cut sets. And what does it mean? It means if component 1 and component 2 fails, then the system fails. If component 3 fails, then the system fails. Basically, with this minimal cut set, if we have safety critical system, in most cases, we are using lots of redundancy, so triplication and so on and so forth. And if we put this redundancy logic in the fault tree gives the possibility to identify these minimal cut sets. And minimal cut sets shows which components the joint failure of which components will cause the failure of the system. And this is very important for the reliability analysis because we can identify them and protect these components. Okay, for example, for this system, the minimal cut set is C1 and C3. If C1 and C3 fails, we have no pass from input to output and our system fails. Or C1, C2, and C4. If these three guys fails, it's also a minimal cut set, the system is failed. Okay, a little bit later we will also talk about the dynamic fault trees. Dynamic fault trees is fault trees plus special gates, and I will explain some of them. So, and basically the solution of the dynamic fault trees is to convert them into a Markov chain, but we will discuss it a little bit later. Okay. The thing is that if we have the static fault tree, we might either do the quantitative analysis and identify these minimal cut sets, or we might do the qualitative analysis and identify the cut sets, or we might want to do the quantitative analysis and compute the probability of failure of the system. And this can be done in several ways. It can be done using the direct bottom-up, top-down methods, or it can be done with specific mathematical frameworks such as binary decision diagram or Bayesian networks. Okay, let's start with a bottom-up, top-down computation. So I took this from this paper. You could find the okay. I will give the exact notation, but even if you Google this guy, this is the recommended paper source. So I will give you another example of the fault tree, and we will use this example for the explanation of the bottom-up and top-down methods. So, and also, by the way, I will show you some additional gates that can be used in the fault tree. Here we are talking about the system that has a power supply, PS. It has two redundant computers, C1 and C2. It has a bus, and it has three redundant memory units. M1, M2, M3, it's memory, computer 1, computer 2, and here is power source. You could see that this power source and this power source is basically the same basic event. We just draw it 2 times in order to avoid the intersection to make the fault tree beautiful, but we know that they are the same thing. It means if this fails, it is the same unit. They fail at the same time, okay? So then the memory is shared between 2 computers. What does it mean? We assume that, okay, we have computer 1, computer 2, computer 1 uses memory 1, computer 2 uses memory 2. If memory 1 fails, we have memory 3, which is a kind of a spare, and then computer 1 start using, instead of memory 1, and start using memory 2. In this case, we have the following configuration here. The system survives if at least 2 out of 3 memories operating, and let's call it memory system. The memory system is fine, or the memory system fails if more than 1 or 2 or more memory fails. In this case, we have the failure of memory system. Then both of these guys, they need the memory system, and the, let's say, computer 1 system fails if either CPU 1 fails, power source, or memory system fails. And computer 2 fails if CPU 2, power source, or memory system fails. Then the entire system fails if both computer fails because they are redundant. Okay, but now there is a special gate. This is the, wait a second, yeah, okay. Another thing that the system fails also if both computer fails or if bus that connects everything fails, because we have only one bus for everything. So here we are, and here is a special gate. It is ingibit gate. And ingibit, what is ingibit is written here. Output events of the ingibit gate occurs if the input event occurs while the conditioned event, this one, the gate also occurs. Basically here we just say that the system fails if the computer fails and the system is currently in use. Because if the system is not in use, so we are everything fine, we are not using it, we don't have a failure of the system. This gate actually behaves like AND gate with two outputs and therefore is treated in the rest of the, okay, so this, because I took it from the paper, the idea, these ingibit gates, we are not using this often, we can really specify it as an AND gate, but sometimes if we have, you know, some, for example, we model the system with some modes, and the system operates in mode A and in mode B, and in mode A we use these components, and in mode B we use that components. And in order to distinguish between the modes in the failure, in the fault tree, we can easily use just, you know, some special gate to distinguish between the modes, for instance. Okay, now how we compute it. So the bottom-up method, it's bottom-up. We start from the bottom and go to the top. We know the probability of failures of these guys. We're using the formulas of parallel and sequential configuration, which I have talked about them before, to go upstream. So using these guys, we compute this guy. Using these guys, we compute these guys. Using these guys, we compute this one, and so on and so forth. And this is bottom up. The top-down method, it's different. We're going from the top to the down, and we try to represent the system, the failure of the system, as a logical formula of the failures of the component. For example, we start with this G1, and we say that G1 is U logical AND, and the combination of B logical OR D3. What does it mean? It means this fails if this is true, and this fails. And this fails if B or G3 fails, and so on and so forth. So we can go down, and at the end we have a logical Boolean formula that represents the failure of the system. And then using this formula, we can also apply this parallel and sequential configuration to the parts of the formula. Or this method is good because this method also shows the minimal cut sets if we will represent this either as a DNF or KNF, I think disjunctive. Yeah, so this formula, if we're creating this formula, we also end up with the minimal cut sets, like with a qualitative analysis at the same time. And then we also can apply different, you know, logical operations to this formula. We can make it simpler, and then the computation will be easier. So that's why if you just have a simple fault tree, you can go, and even with a pen and paper, you can compute it using the bottom up. But usually the software is computing it top down. We, you know, we use, we define the formula and then we compute the formula, usually with some solver. Okay, then these are kind of, you know, direct computation, but we could also use special mathematical methods to compute it, or mathematical models. And the first mathematical model is BDD, binary decision diagram. I already talked about this formula, and binary decision diagram, it's a kind of a way how we can represent the logical formula in a way of a graph. Here is an example how the static fault tree can compute it either using BDD or either using Bayesian network. BDD, Bayesian network. So we start with BDD. Here is a fault tree. Let me give some context. We have a device, we have power source 1, and we have power source 2. Power source 1 and power source 2 are redundant. The system fails either if device fails or if both power sources fail. Then how we create binary decision diagram for this static fault tree? We go through the events according to some sequence. Sequence is important, I will show it later. But these are static fault trees. Static means we don't care about when the component fails. We just care is it fail or not. We don't care about the sequence of failures in the static fault trees. So we don't care will device failure before power source 1 or after and so on. But now in the binary decision diagram, we just take some random sequence. Let's start from the left to right. And basically we are defining, okay, if devices fail, then the system is failed. We come here. But if device is not fail, we checking, okay, checking is not the good word, but we are evaluating will the power source 1 fail or not. If the device and power source both survive, then everything fine. We have 0, 0 means no failure, 1 means failure. So basically, usually ones go to the right, zeros goes to the bottom. So, and we evaluate these events, and we end up with also the graph like this. And the graph basically represents, it is really similar to the tree which I have shown in the very beginning. So let's say, do you remember, for example, this part, power source 1 and power source 2? If both of them fails, the system fails. It's something like we go on the right side of the tree that I have shown. But in this case, we draw these, decision diagrams in a more general way. We are combining parallel and sequential configurations. I will not go in details, but there are strict methods how to generate BDDs from the static fault trees. So, and the most commonly used is the method presented by Antoine Rosy. So, and this is a very efficient method for computing of the static fault trees using BDDs. So, and this guy, he's famous because of this method, more or less. Hello, Antoine. So, basically, if we have the binary decision diagram plus probabilities, we just multiply the probabilities along the way, and we get, for example, here it is just probability of failure of the device, but in order to come here, we need to take the probabilities that device is not failed, source power 1 failed, power 2 failed. That's why it is 1 minus PD multiplied by PS1 multiplied by PS2, right? So, and basically this would be, also two cut sets, right? So one of the cut set is D and another cut set is PS1 and PS2, okay? So that's how I'm just giving you some intuition how you identify the cut set during the binary decision diagram. Here is another example. We also have some two systems which consist of two components sequentially, and then it is AND gate. Redundancy comes here. That's why, okay, we also go through event 1, then event 2, then event 3, then event 4, and we end up basically the systems, for example, fail if E1 and E3 fails, or if E1 and E4 fails. So that's how we define the cut sets. As I told, for the binary decision diagrams, it's very important to go through correct sequence, because we can, for example, consider the blocks like E1, E2, E3, E4, and we will end up with such BDD. But we can consider it like E2, E1, E3, E2, E3, E4, and then E1. And in this case, we will end up with a bigger BDD, and bigger means we need more space to store it, we need more computation to compute it, and so on. So that's why, depending on the order, we will have bigger or smaller BDDs, and our computation will be more or less efficient. So in most cases, if you have some software that can compute fault trees, it already uses some of the methods, like all these ones. and you don't care about how it's done. But if you want to do it in an efficient way, or if you want to develop your own software for the analysis for the fault trees, you will need to think about these things. So the next part for the static fault trees is the Bayesian networks. You can compute the static fault tree also using the Bayesian network. What is Bayesian network? Bayesian network is also a cyclic graph, but and the nodes of the graph, they represent basically the Bayesian networks, they all about the conditional probabilities. They are used to represent the condition of okay, so let me just go through example. For example, we know that the failure of the system depends on the failure of component D, and the failure of the component of the power systems depends on the failure of PS1 and PS2. For independent events such as failure of D or failure of power source 1 and power source 2, we describe them just with a very simple, it's called conditional table of probabilities. No, CTP, conditional probabilities table. Something like that, something with stable, conditional, and probabilities, whatever. So if the event is independent, like the failure of the define, we just define, okay, it will be either okay or failed. And the same for these power sources. But for example, for the subsystem, the failure of subsystem depends on the outcome of these two events. And here, because it is a static fault tree and the things are independent, we just define this with zeros and ones in a very simple way. And here we define the logic of AND basically. If both of them okay, then the subsystem is okay. If both of them fail, then the system fail. And if only one is okay, then the system is okay because it is AND for the failure. I mean, we are using the logical AND in terms of from the point of view of fails. So, but the thing is that with the Bayesian network, you can do more. You can define different probabilities of the failure of the system depending on the outcome of these events. And this is a power of the Bayesian networks. Here can be not 1 and 0, and you can define different probability of failure of the system if one of the component fails. So it could be not one that, let's say, it could be that if power source 1 fails, power source 2 is okay, but the power source 1 fails in a kind of, specific way that the system is still. So, and in this case, it becomes not and or it's not becomes not logical. It becomes also some conditional probabilistic gate that has its own probabilities. So, but it's a little bit too complex. I'll go to that. But what we can really do cool with Bayesian networks, we can model so-called statistical dependencies between the basic events. Let's say it could be that the failure of power source 1 can influence the power source 2. And it could be that failure of the power source 1 can depend on the failure of the power source 2. And in this case, we can represent it with a separate conditional probability table and so on. So, and then basically, also will not go into the method, but the idea we're interested on the system failure. And if we have all these numbers here, there is a method that allows to compute it. For example, we know that the system fails if this is failed and this is okay. So we know this part. In this case, we take the numbers from other, we multiply them, sum them up, and we compute them. But the idea that, so with the Bayesian network, we can model dependent failures of the basic components. If we need to model them, we need to use the Bayesian network. That's the bottom line. Okay, There are different methods for computation of the static fault trees listed here. Here is the standard, and here are some software, analytical software that allows the computation of fault trees. The next method, event trees. It also can be used to compute the reliability of the system based on the reliability of the components. But from the fault tree, in most cases, the fault trees are used to compute the reliability of the system from the structural point of view, and event trees are used to compute the probabilities from the from the point of view of the process. Okay, what is it? It's basically the tree. Tree means that it is just a mathematical graph construction without cycle, and it's just branching from left to right or from top to bottom. In the event tree, we are starting with initiating event, go through several events, and we end up to some outcomes. The probability of the outcome is the result of the probability of the events, and basically we multiply it. It's just, remember the tree which I showed you at the beginning of the lecture, it's the same, but we just have more branching. Okay, so initiating event, motor 1 is okay, motor 2 fails, motor 3 is okay, outcome 3. To compute the probability, we just multiply it because it's sequential. So, for example, that's okay. We could use event trees also to model the structure, but in this case, we will not use the power of the event tree, but I'll show, okay, for example, we have brake pedal in the car, we have a brake sensor, brake controller, and we have the brakes, the actuator. They are connected with or. If sensor fails, we are done. If controller fails, we are done. If actuator fails, we are done. That's how we can represent it with a fault, with an event tree. Brake sensor fails, yes, no. With yes, we go here. With no, we go here. This 0.2 means the probability of the failure of the sensor. And with probability 0.2, we end up here. With probability 0.8, we end up here. Then the brake controller fails. And then actuator fails. Basically, if either sensor, controller, or actuator fails, system fails. That's why all of these outcomes mean the failure of the system. And the brake engages only if we answer no to all these events, right? And the probability that the brake engages will be 0.8 multiplied by 0.9 multiplied by 0.75, okay? So, but the power of the event trees is that the conditional probabilities can be considered. It's like in the Bayesian networks, but a little bit in another way. So because, for example, here, the brake controller, the failure of the brake controller after the sensor can depend on the outcome of this event. Let's say if sensor is fine, then we have one distribution of the probabilities. If sensor is not fine, we can have another distribution of probabilities. These things we can model in the event tree, but we cannot model them on the fault trees. That's the difference. Usually event trees are not used for the modeling of the structure. It's possible, but it makes no sense. The structures can be well modeled with the fault trees, but the event trees are good for the modeling, for example, of some processes, I would say. For instance, imagine we have a building or a room, and it could be a fire inside or explosion inside the building, and we have a sprinkler systems on the ceiling that will try to extinguish the fire with the water, and we also have alarm. And then we try to evaluate, the safety of this system. We know the probability of the explosion, and the explosion is our initiating event. Then, if explosion happened, yes, no. If the explosion not happened, we still could have the probability that we will have fire because of something else. No, sorry. If explosion happened, yes, no. If explosion happened, we have fire. If explosion doesn't happen, we have no fire. If we have no fire, we don't care about sprinkler system, we don't care about the fire alarm. And guys, terribly sorry again, but I hope this will help you to understand it better. The result of the explosion can be either we have fire or we do not have fire, okay? So it's a little bit confusing even for me right now. This is the probability of the explosion. With this probability, we come here, and yes, if there were no explosion, I think it's not really canonical inventory, because we have probabilities here on the nodes, and normally we should have the probabilities here on the arcs. So that's why I would better ignore these probabilities, and I will assume that they are here. And what I want to explain, the process. If we have the fire with some probabilities, the sprinkler system will activate it, and with other probabilities will not activate it. If the sprinkler system is not activated, this is a bad event. The sprinkler system doesn't function, and it could be that in this case the fire alarm will be not activated, and in this case we will come up with the most critical damages. I mean, it was an explosion, we have fire, sprinklers cannot extinguish the fire, and we cannot tell the people using the fire alarms that the people need to go outside. And here we have really critical damage in this case. If we go on this way, and we will multiply the probabilities on this way. But if we go, for example, this way, like we have fire, but the sprinkler system works and the fire alarm works, we could have some damage, and they separated to the minor damage, major damage, and critical damage. We are in the context of damage, and we can compute these probabilities during the inventories. Okay. I don't have example on this slide, but also, do you remember this quadrocopter example from the previous lecture, where we have a quadrocopter? We might say that this quadrocopter has a mission. It has a takeoff, it has a transfer of flight, and it has landing. And in each mission phase, it can be that the probability of failures for its components could be different. And that's why also we can use the event trees to model the phases of the mission, okay? So we use, and in this case, we can really combine fault trees and event trees. We use event trees to model the phases of the mission, and we use the fault trees to model the components. So basically, let me show this example. They are not in the slide, but I have it in my computer, hopefully, in one of the papers. So, I mean, for example, we can have a system of the quadrocopter that starts, flies, lands, and even might have some emergency landing. The quadrocopter itself, the reliability of the quadrocopters that consist of hexacopters that consist of 6 motors, battery, controller, and time view, we can model it with a fault tree, right? So, but these probabilities could be different for the different phases of the flight. And the mission itself, we can model with an event tree. So, for example, the mission phase, let's say the flight, we can model with an event tree, and that's how we can combine. And usually this is the case. we are combining the different methods, and here we're combining event trees for the definition of the mission and the fault tree for the computation of the reliabilities of the system for different mission cases. Okay, I think I will stop for today because next time in the next part of this lecture 4, I will talk about the Markov models and Petri nets. Thank you for your time. I will continue on the next lecture.